Okay, we're just going over the review that Honors has for their reactions in the Stoich test. There are three major concepts on this test. One is predicting products based on the reactants and then writing and balancing the equation. The second is percent yield calculations, and the third is limiting reactants. So for percent yield, we have the equation percent yield is equal to the actual yield divided by the theoretical yield times 100. The actual yield always comes from experimenting. That's what actually happens when you do the experiment. The theoretical yield, on the other hand, is a calculated value based on your starting materials. So you look at how much you start with, and you use stoichiometry to predict the maximum amount of product total possible, and then you are able to compare that to what you get when you actually do the experiment. And so this is a measure of the efficiency of a chemical reaction. So how good is our experiment is basically what percent yield tells us. So I'm just going to I've already got the answers on here for you. I'm going to kind of walk you through how I got there. A couple of tools that the kids will have for their test. One of them is the reaction rules. They will have a copy of that. They don't have to memorize it, but they do need to know how to use it. So we're going to do a little bit of talking about how to use that. The second thing is the common oxidation numbers. Because our in a covalent compound, our nonmetals are going to have more than one possible oxidation state, and so we have to be able to predict that. And of course, the third thing is a polyatomic ions chart. So let's start with calcium carbonate yields. So we have CaCO3. A single reactant always indicates that this is going to be a type of decomposition. Anytime there's just one reactant, that is a red flag that this is going to be decomposition. The problem is there are 4 types of decomposition reactions according to our reaction rules. We have decomposition of a binary compound, decomposition of an oxy acid, of a base, and of an oxy salt. What's nice is the reaction rules tell us exactly what those things are. Binary compound just means made of 2, so if you have a compound that's 2 things, you just take it apart. Oxy acid is hydrogen with a polyatomic ion containing oxygen, so things like H2SO4, HNO3, H3PO4, all of those are oxy acids. Decomposition of a base, that is a metal with a hydroxide, so NaOH, BaOH2, KOH are all metals. And then an oxysalt is a metal with a polyatomic ion containing oxygen. So Na2SO4, AlPO3, those are all going to be your oxysalts. So calcium carbonate, in this instance, we have a metal with a polyatomic ion containing oxygen. So that is going to be the decomposition of an oxysalt. And then this tells you exactly what it's going to make. It yields a non-metallic oxide and a metallic oxide. So what we're going to do is we're going to go to the original formula. Our metal was calcium, so we're going to put the metal with an oxygen, and then our non-metal, carbon, with an oxygen. Now, with the metal and the non-metal, we crisscross our normal charges. So calcium's 2 plus, oxygen's 2 minus. They cancel each other out, so CaO is our correct formula here. The way I arrived at the CO2 is by looking at what the polyatomic ion is. Okay, CO3 is carbonate with an ATE, and if you look at this note down here, 8 polyatomic ions mean we're going to use the high oxidation number on the nonmetal. So if we go to carbon on our list, carbon has, this is its ionic charge. We're not going to look at that. So when it's in a covalent compound, its charges are 2 and 4. The high oxidation number would be the 4. So when I did this formula, I used 4 plus for carbon and I used 2 minus for oxygen. When you reduce that, you end up with 2 plus for carbon and 1 minus for oxygen, and then you just simply crisscross that, and that's how I arrived upon the CO2. This equation was already balanced, so there was no need to add any coefficients. So for letter A, it says this reaction was done in the lab with 3.45 grams of calcium carbonate. What would be the theoretical yield of calcium oxide? So this is just a basic gram to gram stoich. We start with the reactant that they've given. They've asked for a theoretical yield, which remember I told you is a calculated value, specifically of the calcium oxide, so that particular reactant. So this is just a gram to gram stoich going from grams of calcium carbonate to moles of calcium carbonate, moles of calcium carbonate to moles of calcium oxide using the mole ratio, and then moles of calcium oxide to grams using the molar mass of calcium oxide. That got us the 1.93 grams of calcium oxide as our theoretical yield. Then it asks if 1.52 grams of calcium oxide was actually obtained, so that means in the experiment, what would the percent yield be? So in this problem, they've given us the actual yield. We just calculated the theoretical yield here. So we're going to use this equation, actual over theoretical times 100. So I took the 1.52 grams from the experiment, the 1.93 theoretical yield times 100. That gives us 78.6% calcium oxide. All right, for our second problem, we had iron and copper 2 sulfate. So we had Fe and then CuSO4. The red flag here is that we have an element all by itself. Anytime we have an element all by itself with a compound, this is going to be single replacement. Okay? So what's going to happen in a single replacement reaction is the element that's by itself is going to find a similar element in the compound and kick it out and replace it. Okay? So the iron kicks out the copper because iron's a metal, copper's a metal, so iron's going to kick out the copper. So we're going to end up with copper by itself and the iron with the sulfate instead. The important thing over here is that we re-crisscross charges. We don't know the charge of iron, so we're going to use what's called the preferred oxidation number. We have that on this list on the reaction rules. Iron's preferred oxidation state is 3+. So when it comes over here and it's in a compound with the sulfate, we use the 3+ charge to get this, and then of course sulfate has a charge of 2-, so that's Fe2SO4 3. And then the copper by itself, we add coefficients to balance the equation. So we had 2 iron, 3 sulfate, 3 sulfate, 3 copper, 3 copper. Then it says, a scientist performed the above reaction, was able to get a percent yield of 92.5% copper when she used 1.45 grams of iron and 6.54 grams of copper 2 sulfate. So they've given us specific amounts for each of our 2 reactants. Then it asks, what is the limiting reactant? So the limiting reactant is the one we are going to run out of first. So the way to figure this out, I went from reactant number 1 to reactant number 2 in this problem. There's more than one way to do this. You could also go from reactant 1 to a product, reactant 2 to a product, and then compare how much product you made. I chose to do this method. So if I'm going to use up completely all 1.45 grams of iron, this is just a gram to gram. I went from grams of iron to moles of iron, moles of iron to moles of copper sulfate, moles of copper sulfate to grams of copper sulfate, straight up gram to gram. That gets me 6.22 grams of copper sulfate. So if I'm going to use up all of the iron, I'm going to need at least 6.22 grams of copper sulfate. I have more than that. So that means that I'm going to be able to completely use up all the iron, and I'll have some of the copper sulfate left over. So that means that your iron is the limiting reactant here. Okay? Then it says how much of the excess reactant will be left over. Well, we're going to use 6.22 grams of the excess reactant. That's the copper sulfate. We started with 6.54 grams, so 6.54 minus the 6.22 that we're going to use gives us 0.32 grams of the copper sulfate remaining left over. Then it asks, what would the theoretical yield of copper be? So the limiting reactant is always going to determine our maximum amount of product. So I'm going to take that 1.45 grams of iron because that's my limiting reactant. And this time I'm going to go to the copper. So I'm going from grams of iron to moles of iron, moles of iron to moles of copper to grams of copper. The maximum amount of product I should be able to make is 2.48 grams of copper. So whenever you're trying to figure out theoretical yield, that's also known as max product. You're going to want to start with the limiting reactant. Okay? That's really important. You always start with the limiting reactant there. And then what was the actual yield of copper in grams? So way back up here at the problem, they gave us a percent yield of 92.5. We know the theoretical yield because we just calculated it. So they're telling us to find the actual yield. So this is just an algebra problem. We have percent yield is equal to actual over theoretical times 100. I divided both sides by 100, and that loses the 100 over here. That left me with actual over theoretical is equal to percent over 100. So I multiplied both sides by t to get rid of t over here. So our actual yield was the theoretical times the percent yield divided by 100. So I have all those numbers. This was given in the problem, or no, sorry, this is what I just calculated up here. This was given in the problem at the top, divided by 100. Our actual yield of copper in the experiment would have been 2.29 grams of copper. Then we have water and sulfur trioxide, so H2O and SO3. This one is tricky. Here's the red flag here. The red flag here is water. We have two compounds, and usually two compounds means double replacement, but it can also be a type of synthesis reaction. And when we have water, it is likely that this is a synthesis reaction. There are two types of synthesis reactions that involve water. So let's come over here. We have the formation of an oxyacid involves water and a non-metallic oxide, and the formation of a base involves water and a metallic oxide. In this case, sulfur is a nonmetal, so this is a non-metallic oxide. So we are going to have the formation of an oxyacid. What's cool is this tells us exactly what that's going to look like. It's hydrogen with a polyatomic ion containing oxygen. So I put my hydrogen first, I put the oxygen at the end. The non-metal that I had was sulfur, so I added the S. Now, how did I know that it was SO4 and not SO3? Because we have two options with sulfur. We have two polyatomic ions with sulfur in them. They are sulfite, which is SO3, and sulfate, which is SO4. So how did I know which one to choose? Well, it's based on the SO3 over here. We know that oxygen's charge is always 2 minus. I call it the bully. Oxygen is one of the only nonmetals that keeps its charge no matter what. It's always 2 minus. And there's 3 of those for a total of -6. That means that the charge on this sulfur has to be +6. In looking at our oxidation states, +6 is the high charge for sulfur. And according to rule number 1 on our reaction rules, the high oxidation number means we're using the 8 polyatomic ion. So that's why I use the SO4, because that is sulfate. And then, of course, sulfate has a 2 minus charge, so I crisscross to get the 2. And this was already balanced. So this experiment was performed using 5.43 grams of water and 6.78 grams of sulfur trioxide. Which of these is the limiting? So again, I did reactant 1 to reactant 2. To figure out which one was limiting. So I started with the water. It doesn't actually matter which one you start with. You could start with either one. So I started with the water, went to the other reactant using a Stoich, and that got me 24.1 grams of sulfur trioxide. So if I'm going to use up all of my water, I need at least this much. I don't have anywhere near that. Okay, so that means I'm going to run out of the sulfur trioxide first, long before I would ever run out of water, because I have enough water to make, to use up 24.1 grams of sulfur trioxide. So that means the sulfur trioxide is our limiting reactant. So then it says, how much of the excess would you have left over? This time, I don't know, because the calculation that I just did was, didn't tell me which one was, or didn't tell me how much of the excess I was going to actually use. It told me how much of the excess would be needed. So in order to figure out how much of the excess we would have left over, I'm going to start with how much of the excess I actually started with. So that's the amount that was given in the problem. And so now I'm going to go from reactant number 2 back to reactant number 1, because we know we're going to use up all of the water. So this is going to tell me if I use, or excuse me, we're going to use up all of the sulfur trioxide. So this is going to tell me how much water I'm going to use up all of the sulfur trioxide. I'm only going to use 1.53 grams of the water. The original problem stated we had 5.43 grams of water. So I'm going to subtract out the 1.53 grams we're going to use. That gets me 3.9 grams of water left over. And then the next question, how much of the excess would you have used up? That's what we just calculated here as the 1.53 grams. So we don't actually have to do another calculation. this answered both of those questions. Maximum amount of product you could form. Remember, that means we need to start with the limiting reactant because the limiting reactant always determines the maximum amount of product. So we start with that 6.78 grams of SO3, and we're just doing a gram to gram Stoich to get to the product, which is H2SO4. And that gets us a maximum product of 8.31 grams. Remember that this is also the theoretical yield because it is a calculated value. So this is max product, but it's also theoretical yield. All right. Chromium 6 oxide and water yields. All right. Boop. That should be a 3, y'all. Because this is 6 and 2 minus. If we reduce that, we get 3 and 1. So that should be CrO3. And that should be a 6. My bad. And we'll need this to be a 3. There we go. That is much better. All right. So chromium 6 oxide, CrO3 plus water. Water here, again, is the red flag. That tells us that this is likely synthesis, even though it has 2 compounds. 2 compounds normally being double replacement, but synthesis often has water as one of the reactants. So here we have 2 types of synthesis with water, either the formation of an oxy acid or a base. This time, however, we have a metallic oxide with water. So this time we're going to form a base. So we're going to have the metal with the hydroxide. So that's why I put the chromium with the hydroxide. The chromium is going to keep its 6 plus charge, and that's why it's CrOH6, okay? So then it says, if a student achieves a 56% yield for this reaction when 4.56 grams of product was actually formed, what was the theoretical yield? Now, we don't actually have to do a gram to gram Stoich here because they didn't give us any reactants. They've told us what was actually formed in the experiment. So there's our actual yield. They've given us the percent yield. So we're trying to calculate theoretical yield. This is a little tricky. So I'm actually going to walk y'all through the math real quick because this one is the one that kids usually get wrong. The problem is we're solving for the bottom of a fraction. So actual over theoretical times 100. We want this number down here. Being on the bottom of a fraction, what kids usually end up solving for is 1 over t instead of t. Not great. So what we're going to do is we're going to divide both sides by 100 to get rid of this. Now, rather than multiplying by t, because that's going to get us a little confused, I'm going to take the reciprocal of both sides, which means to take both fractions and flip them over. The notation for this is parentheses 1 minus. And so that's going to turn this into 100 over percent yield is equal to theoretical over actual. So I just took this and flipped it over and this and flipped it over. As long as I do the same thing to both sides, we okay. Then I can simply multiply both sides by A to get rid of that over there. So the theoretical yield is equal to the actual yield times 100 divided by your percent yield. Okay, so that's the math behind how to get there. And that is what I did here. So I got this equation there. And then I plugged in the actual yield that was given in the problem, 4.56, multiplied by 100 and divided by our 56% yield. That gets me 8.1 grams of CrOH6. All right. Almost there. Dinitrogen pentoxide, so N2O5, yields. So now this is red flag. There's only one reactant, so that means that this is going to be a type of decomposition. Okay? Now this one is really straightforward. It's going to trick them because this is a nonmetal oxide, but that's actually one of the products of a decomp, not one of the reactants. Okay? Non-metallic oxides are the product of decomposing an oxyacid. What we really have here is just a binary compound. So we're just going to take it apart into its 2 elements. So the N2O5 comes apart into N2 and O2 because both nitrogen and oxygen are Hofsprinkles. So when they're by themselves, they're N2 and O2. And then we just added a 2, a 2, and a 5 to balance the equation. Question A says a student performs this reaction above and obtains 3.4 grams of the nitrogen gas. So there's our product. If he started with 15.6 grams of dinitrogen pentoxide, what is the percent yield? So in order to calculate percent yield, we need the actual, which was given, okay, because that was the experiment. But we also need the theoretical, which this is not, because this is a reactant, not a product. In order for it to be a theoretical yield, it has to be a product. This is a reactant. So we're going to do a gram to gram calculation to go from the grams of dinitrogen pentoxide to grams of nitrogen. It should have a matching unit, grams of nitrogen, with the actual yield. So actual yield and theoretical yield have the exact same unit. They should both be grams of the same compound. So once I've done that gram to gram, there's my theoretical yield. So I can take my actual yield that was given in the problem as 3.4 divided by the theoretical yield, which we just calculated, times 100. That gets us a percent yield of 46.7%. What a terrible experiment. Now, thoughts onto why this might have not been a great yield. This is a gas. So chances are we thought we were doing this in a closed system, but we were not. So it looks like some of our nitrogen gas leaked. And then on our last problem, we have magnesium hydroxide, MgOH2, and phosphoric acid, H3PO4. So we have two compounds. There are no red flags on this one. There's no water in this one. So when we have two compounds, that's typically double replacement. That means that my two cations, the magnesium and the hydrogen, are going to swap places. So when the hydrogen comes to be with the hydroxide, that makes water, which of course we know is the same thing as HOH. The magnesium goes with the phosphate. We crisscross the charges. So the 2 from the magnesium goes over there. The 3 from the phosphate goes over here. It says the above reaction is performed and a white cloudy precipitate forms. Which product is most likely the precipitate, and how do you know? A white cloudy precipitate is a solid. Okay? So the only option of our two products, we know water is going to be a liquid. So the only option here is the Mg3PO42 because the precipitate is a solid and H2O is a liquid at room temperature. All right. So I hope that helps you guys to be prepared for the test.